At this point in the module, I've introduced you to several quantities which can be used to describe the motion of a mass oscillating at the end of a spring. These quantities include the period of the motion. The period of the motion is the time it takes the mass to make one complete cycle of motion. We've seen that the period is equal to 2 pi times the square root of the mass divided by the spring constant. We have the frequency of the motion. The frequency of the motion is the number of cycles of motion per time. The frequency is equal to the reciprocal of the period, which is 1 over 2 pi times the square root of the spring constant over the mass. And then we have the angular frequency. The angular frequency is equal to 2 pi times the frequency, and that's just equal to the square root of the spring constant over the mass. In this video, we're going to do a short example just to start getting used to these formulas here. So here's the example. We have a 500-gram mass, which is attached to the end of a spring. The spring constant of that spring is unknown. So imagine that we do an experiment. Imagine that we take the mass, grab it, and then pull on the mass so that the spring extends, and then release the mass, and then time how long it takes for the mass to make 10 complete cycles of motion at the end of the spring. And suppose that having done that experiment, it takes 8.30 seconds for the mass to complete those 10 cycles of motion. We would like to find the period of the motion. We would like to find the angular frequency, and we would like to find the spring constant. As I said before, this will be a fairly straightforward computation, so I would actually encourage you to pause the video and try all of this on your own before rejoining the video to see what I do. Okay, part A. What would be the period? The period of oscillation is the time it takes to make one complete cycle of motion. Here we are told that the time for 10 cycles of motion is 8.3 seconds. So the time for one cycle of motion would be 8.30 seconds divided by 10. And that would be 0.83 seconds. For part B, we want to find the angular frequency. Notice from here that the angular frequency is 2 pi over the period. So I'll just copy that equation and then substitute in this value for the period here. So we have angular frequency is 2 pi divided by 0.83 seconds. So put that in your calculator, and I believe you will get 7.57. And then we can just use inverse seconds, or seconds to the -1, as the unit. Now for part C, let's try to find the spring constant. And probably the most convenient way to do this is to use this formula, which relates the angular frequency to the spring constant and the mass. So I'm just going to copy that over. We have angular frequency equals square root of k over m. So let's square both sides. We then have omega squared equals k over m. So let's solve for k. K equals omega squared m. And let's make our substitutions. Omega was 7.57 inverse seconds squared. The mass was given as 500 grams, but I'm going to convert that to kilograms. So we have 0.500 kilograms. Now, when you plug into your calculators, the numerical value will be 28.7. We can see here that the units will be kilograms over seconds squared. We could leave the units like this, but it's more conventional to express the unit for spring constant as newtons per meter. So let's see if we can get this into newtons per meter. So let's just say I start with kilograms per second squared and then multiply by meters over meters, which is just multiplying by 1. So notice here that we have kilograms meters per second squared, which is a newton. So we can see then that kilograms per second squared is just newtons per meter. So we can then say that the spring constant is 28.7 newtons per meter. So this has just been a simple warm-up to try and get used to these formulas here. In the next video, we're going to get a bit deeper into how we describe the motion of a mass oscillating at the end of a spring.